This presentation looks at forensic computing. Okay, so let's analyze our organizations and our technical infrastructure. Basically, at the top level of any company should be ethical and cultural considerations. It is important that these considerations map directly onto the laws of the land. Then, inside the laws, we can define a policy, and from our policy we then generate procedures. From these procedures we then implement our technical specifications. So if we look at this mapping inside an organization, at the core we typically have storage, processing and communication. Around there we have operational procedures, and above that some administrative and management processes, and then at the outer regions we have legal considerations and eventually ethical, cultural. So basically we have the laws of the land, and it's obviously up to the judicial system, the governments, to lay down these laws, and these are typically then implemented as policies inside the organization with defined procedures and then implemented in some technical way. A key factor is that the legal system, if it's required, defines the rules and responsibilities, and it is up to technical professionals to be able to report and advise. If an investigation goes to legal proceedings in a court, it is important that the IT professional operate as professionally as possible and does not assume guilt in any way. It is obviously up to the legal process to define that if this is true or not. So inside our network we typically have some sort of perimeter with a firewall, and most of the time we're dealing with security, and the security might be mapped to some audit or security policy. For this we define event detection, network sensors, servers and logs on servers, event logs, host logs, and so on. But sometimes we actually need these logs and these events in the form of a digital forensics investigation. When this happens, we need to make sure that we follow the correct procedure, which is typically collection of data, preservation of it, analysis and reporting, or CPAR. And this is where security differs from digital forensics. So when an incident happens, we typically have the following procedures. To make sure that we have the correct procedures in place, we need to make sure that our organization has a pre-incident preparation. And for this we typically define a number of scenarios, a number of risks that may happen, and then we can define all the procedures which relate to that incident. One part of this is how we actually detect the incident, so it might be in the form of network sensors or event logs. Then when an incident has been detected, we then typically go into an initial response phase, and hopefully if we've designed our procedures correctly, then the procedures will be used inside the response. In many cases, a team will be set up to basically formulate the response. If the investigation is to go ahead, then there is typically some form of data collection, onto some form of analysis, and then onto a reporting procedure. It is key at each of these stages that the senior management and the legal elements are kept up to date on each of the basic procedures. and an action should be agreed to allow the process to go from one stage to the next. To forensic tools. So our basic procedures that we have are the pre-incident, the detection of incidents, initial response, formulate response, data collection, data analysis, and reporting. So in the pre-incident phase, we prepare a whole lot of possible threats. We then define the processes and our responses to them, and then prepare the documentation that is required to make sure that the procedure is followed. It is important that everyone in the company understands these procedures and the reasons for implementing some form of investigation. With the detection of incident, we can have many. We could have data stealing, email, spam, harassment, embezzlements, denial of service, and so on. So there is a whole lot of events that we might want to detect. Then, with our initial response, we typically report the incident and then create a report team of which we should define the basic processes and activities for it. A key part of this procedure is to notify management of the incident occurring, and an incident report is then created. It is this incident report which will be used to document each of the main stages after this. Then, to define how we're going to formulate a response, this might be related to civil, criminal, or even administrative actions. Again, we seek approval from management to go to the next step. The data is then collected and then analysed, and then finally we create a report with defined conclusions and the steps required to go forward and hopefully stop the incident from happening in the future. The first part of a digital forensics investigation is typically the collection phase. In the collection phase, we may have a formal method of picking up the logs and events from across the network, or it might involve going out to each of the devices to find some trail of evidence. So in this case, we might have event logs on machines. We might have a formal syslog server where logs are actually sent to it and it collects the data. We might have web logs, email logs, FTP logs, proxy server logs, router logs. We might have trails from IDSs and domain logs. So overall, we can have many forms of data that can be collected. In the past, the evidence is typically focused on individual machines or hosts, but more and more, as the internet has been used, the trail of evidence is typically spread across a whole network. So one method we can use is a syslog server, and the syslog server allows us to take events from our devices and put them on the syslog server so that they can be played back. The advantage with this is that the actual device, which is logging, does not have to store the logs for any amount of time, and we can gather multiple logs from multiple devices onto a single syslog server. On a Cisco device, we can enable our logging and then define the address of the device that we want to log. After that, we can define what level of severity that we want to log. So we can go for basic alerts, critical conditions, debugging, emergencies, and so on. So in this way, we can filter the logs which are received. The port we typically use on a syslog server is 514, and in this case we're using the syslog server at this address. So when we look at our syslogs on our server, they will look something like this. We typically get the date and the time, the basic priority level, which obviously relates to these levels, the host name it came from, and basically what the message actually was. So in this way we can pick up users logging into network devices, errors being caused, or possibly any malicious intent. Another place we can look to actually get a picture of or a timeline of an event is to look in the event logs. So the three main event logs that we have on Windows are application, security and system. And in here we can actually see a basic timeline of the main events which happened on the machine. Obviously event logging needs to be enabled for the event log to show these events. The credibility of the event log is also questionable as it is a closed standard. So in this case we can see all the events which happened within the application log. Then in the security log we can actually see again a timeline of events and the basic information for them. And then in the system log we can see when users started up the machine, stopped it and logged in and so on. The logs themselves are kept in the system32 config folder, and we can see here our security log, our system log and then our application log. These EVT files are read in and logged to by the service which looks after event logs. The problem with them though is that they can be modified by an administrator or a user on the machine. So we can see in this case that the user has obviously put the clock forward on their machine and then has entered two new commands and put the clock back again. The other problem that we have with event logs is that users can often delete the whole of the event log. So we can see here the user has deleted the event log and then has managed to clear all the events within it with only a message to say that the event log was cleared. So from a digital forensics point of view, it can often happen that a user can cover their tracks by changing the event log. A key process after the collection is to preserve the data that has been collected. So what typically happens is that the data is timestamped for the files that are to be investigated, and then to make sure in the future that the data that we have is still the data that was stored, there is typically a hash signature taken of the data. Then the data is mirrored onto some other device such as a CD-ROM or a USB stick or stored over a network and is thus stored. For the hash signature, we can either take a hash signature of all the data, or we can take a digital signature of each of the individual files. So once we have this, we can make sure if we view the file at some future time, then we check the hash signature to make sure that it's still the same. If for some reason someone has modified the file, then a new hash signature will be generated. So we typically get a hash signature for each file and also a hash signature for the whole of the data. If the hash signature for all the data stays the same, then it's unlikely that any of the files will have changed. So what we typically do is that we have a basic procedure where the investigator goes to the machine, runs a script, and makes sure that that has been validated. So in this case, an automated script might be to get the IP address, the MAC address, and some other details from the machine, get a complete directory listing, take an MD5 signature of each of the files, and zip the whole thing up into a zip file. We would typically also make sure that this was encrypted with some secret key. So we can see here that we're getting the date echoed into the text file. Then we echo the time into it here, and the basic IP config details for the IP addresses of the machine, and then dir/s will take a list of all the files in the folders and all the subfolders. Then we take an MD5 signature of each of the files and write that to the text file, and then zip up all the files into it. Then this file is then sent over to backup storage. A key element for an investigator is to search for evidence of data hiding. So in this case, it may be that a suspect has hidden some data somewhere on a system. The basic forms of data hiding that we have are covert channels, and we'll see those in a little while. We can have stenography, and stenography is where things are hidden inside perfectly legitimately looking content. We can have anonymity and copyright marking. With copyright marking, we can have different forms of copyrighting inside our content that typically looks at fingerprinting and watermarking. So we might have a graphic and there is some fingerprint added to the graphic, either which can be viewed or could be hidden. So we can have an invisible watermark, or we can have a visible one. So one example of how a watermark or hidden content can be added to a graphic is, in this case, we have two layers. We have a bitmap, and we have one layer, and we have two pieces of content. We have some text and a background graphic. One way to hide the text is obviously to change its opacity level. So in this case, we take the opacity down to 50%, and we can see here that it is starting to become invisible, and then we take it right down to 10%, and we can hardly see the text in it. So one way that we can make things invisible is to take the opacity down to 0. Another technique that a user might use to cover the tracks is obfuscation. So with obfuscation, we might have this graphic here, and this graphic here has some sort of meaning. So the user possibly wants to hide the graphic. So obviously one thing they can actually do is to go for a multi-layered approach where there is another graphic over the top of it. The graphic itself is still in the file and still there, but as far as an investigator can tell, the graphic has now been obfuscated. Another method that a user might use in an investigation is to make the image so small that it's almost impossible to see it. So in this case, we could shrink the graphic down into even just a single pixel. So the graphic itself is still there, but has been shrunk down to a small size. You can see here that when we zoom back up, the graphic is still there. Another method that a user might use to obfuscate for an investigation is to change the name of files. So in this case, from a GIF file to a DLL file. And then when an investigator is looking for GIF files, they will not find this graphic file as its name has been changed to DLL. Luckily, we can pick up the basic signature of files on a disk, and basically for a GIF file, all GIF files start with GIF 89A, or most will start with this. There is another format, but all will start with GIF. If we look at an example of this, so we can see here that we can open up a file. So we're going to open up a GIF file, and we can see there that the first few characters are GIF89A. And in this case, this is a GIF file. So even though the name of the file was actually changed, we can still see the file signature. The other thing is that a user might have deleted a graphic from the disk, but all that happens when a file is deleted is that the first character is knocked out in the file allocation table, and the complete contents of the file are still stored for as long as the system doesn't overwrite that part of the disk. So an investigator might do a search of the disk and will not find anything, because a search will typically look in the file allocation table. But a deep search of the disk, which will scan byte by byte, will be able to identify the signature of GIF89A, and then identify the actual graphic stored on the disk. Even though it has been deleted, it still can be there, or parts of it can be recovered. When we look at JPEG files could be changed, but again we have a standard header that we see. FFD8 is the standard start. We have a couple of bytes after that, and then we see the standard signature of JIF, and we can see this from a file, hopefully. So we have a file here, so we have FFD8, and then we have JFIF. This is the standard header that goes on to a JPEG file. Also, what we can get is that even when content has been added into another package, most packages will retain the original metadata which is stored in the file. So in this case, a PowerPoint presentation has used a graphic called cookie transparent 32 colors.gif. It is then added to the PowerPoint. But then we can see when we actually analyze the PowerPoint file that the metadata for the graphic is still there. A key factor in this is that a search for the original file name will not result in a success, because the characters have been stored in a 16-bit format. So we have C here, and then we have a 00, and then we have O, and then a 00, and so on. So the search of the disk requires us to look at a 16-bit code to try and find the file name. Zip files, the user could change a zip file into another type. With this, we typically see the PK starting 2 bytes, and this is the standard format for a zip file. So if we can view a zip file here, we can see here B504B at the start. We can also see the file names, and in this case one of the file names is go.bat. So it's possible to look at each of the file names within inside the zip file. So we can see here in this case we have chap1_2.pass, and this shows us the example where we can see within inside our zip file we have the contents of each of the file names. Stenography is also another method that a user might use to hide data. So if we take an example of a GIF file here, with the GIF file we have what's called the color table, and the color table is stored around this region here. So it's possible for a user to modify the text within inside the color table to pass a secret message. So in this case this graphic has been changed so that a secret message has been added to the GIF file, and we can see here that only some of the pixels have actually been changed. So we can only see this because the message has been poorly added and because we've zoomed in for the message. So we can find our graphic. Here we go. So the actual message has been added into the color table. What will happen is that some of the colors will change their color. So in this case the color that was there has now been changed to a darker color. The same can happen for JPEG, and with a JPEG image it is possible to add a message, and we can see here the original JPEG file, and this is what it looks like after the message has been added. And the way it does this is that JPEG typically splits an image up into pixel blocks, and then it takes each of the pixels within there and then does a frequency conversion on it. So if there are fast moving pixels within inside the block, then we see elements up in this part of the frequency spectrum, but if they are fairly slow moving, then we will typically see the conversion at the lower frequencies. Most images have their conversion in this part of the region, and the reason for this is that if we zoom in, then there isn't really much change for each of the elements. Along with this, the human eye doesn't actually detect a great deal of changes of individual pixels. So a covert message can be sent by actually adding the message to the high frequency elements of it. Then when it is actually converted, then there might be small changes on a localized basis purely for that pixel block. But most users will never look at the detail within inside the image. So we can see here this is a zoomed up version. We can see there that the image has been added in this pixel block, so there are some changes. But as far as the user can tell, there is no change at all, but the covert message has been added, and in this case it doesn't do any good to do a text search within inside the JPEG image. Another method which might be used is a covert channel, and covert channels have been around for many hundreds and thousands of years. So we've typically seen it in transferring briefcases between people and also storing information on microfiche. So an example of a covert message is this one. So let everyone tango. This is Edward's mind in some simple inquiry of nothing before everyone gets into nirvana. And the covert message here is basically just to use the first letter of each of the words. So in this case, when we reveal that, it says let the mission begin. And covert channels are typically used when there are two suspects and they know that they are being observed. So their bank records are being looked at, their internet communications, there are wiretaps, their email message are looked at. So they know that they are being watched all the time and listened to. So they will try to send each other a covert message without these entities finding out what the covert message actually is. So the two ways to do this is either for the suspects to store information at a certain place, and then for the other suspect to come along and read the message. So there is no direct communications between the two suspects in this case, but there is a storage channel. The other method might be in the form of a covert timing channel. In this case, the suspect might start a process, the other suspect detects that it's going, and then start another process, and the other suspect detects it. So in this way, information can be transferred between the two suspects. It is our aim as digital forensics investigators to make sure that we can actually detect these types of activities in some cases. One form of a covert channel is IP and TCP Covert Channels. With this, the IP header and TCP headers were created a long time ago and were typically created with fields which actually didn't do too much. So we might have identification, time to live, and a fragment offset. These are three fields in which someone could actually add information to and which would be hidden from from anyone listening to the traffic. The same again in TCP, the urgent pointer and the data offset are fairly redundant fields and can be used to pass data. So it could be that if a user wanted, they could send in one packet an H for the time to live, then the next packet they might send an E, next packet an L, next packet L, and then next packet O. So they could send the word hello with inside 5 data packets. Anyone listening to the network traffic will think that it looks perfectly acceptable. So we can see here an example of the identification field. So it is used to make sure that each IP data packet is unique from the last. There is no defined standard as to what the number should actually be. In MS Windows, all that happens is it starts with 0 in this case, and then is incremented by 1 each time. On the Sun Solaris, we can see here that occasionally it takes a large jump and then back again. For OpenBSD, we can see here that the identification field has not been used at all. When we look at some other servers, we can actually see activity of covert channels. In this case, we can see an IPv4 server actually transmitting information through the identification field. Another form of covert channel is a DNS Covert Channel. And in this case, Bob and Alice are communicating through DNS requests, and someone might be monitoring it, but their exchanges can go unnoticed. So in this case, Bob makes a request to a DNS server and requests fred.com. So the request goes out and the local DNS cannot find fred.com, so it goes up to the root level. Then it will go to the domain which actually controls fred.com. Eventually it comes into fred.com's domain, so in this case it is Alice who runs that domain. She has registered it with her address for the web server, and then the reply comes from her DNS, goes back up, and then is sent back as a reply to Bob. So if we look at the process again, Bob requests to his local DNS for fred.com, a site which is run by Alice, goes to the local DNS, up a layer to the root DNS, and then back to the domain. There is a domain server there which is looking after this domain, and it sends back what the IP address is. So if we look at another example, so it could be that that Bob contacts the DNS server, in this case for fred.com, but this time he uses Alice's IP address as his source address. So then the local DNS server thinks that the request is from Alice and sends the reply back to Alice. So in this way, Bob and Alice can set up a timing channel between themselves, just as the last one can also be a timing channel. In this case, the timing channel, there is a certain age at which all the DNS requests are timed out, so that Bob can re-request from Alice after a certain amount of time, and it will come back to Alice's domain again. Another example is that Bob might send a request. So in this case, he sends a request for this server, this host, and it's inside the fred.com domain. So what he's done is he's hashed this message, hello, how are you? So this is the base 64 hash of hello, how are you .fred.com. The request then goes out, again it goes back to Alice's domain. Alice then reads and hashes the message, hello, how are you? Then she sends back the hash equivalent of I'm fine and you, and sends the reply back as this. DNS is a fairly dumb protocol in that whatever is replied back will actually be sent. So in this case, this message goes back, and Bob and Alice have managed to pass a message. Another one is that we might have a non-recursive lookup. So in this case, Bob makes a request to a strange domain. If the strange domain is not in the local cache, it will go and request from the other levels and eventually find it. It will then be stored in the local DNS. Next, Alice asks the DNS server for the same domain, and these have been pre-agreed by Bob and Alice, and asks it for a non-recursive lookup. A non-recursive lookup will stop the local DNS from requesting up the levels and will only look in its local cache. If it exists, then Bob has been there already, so Bob passes a 1. If it doesn't exist, it means it's been aged out and Bob hasn't requested it, so it is a 0. So in this way, Bob and Alice have set up a timing channel. Another area that we can have a covert channel is in an application layer covert channel, such as in HTTP. So the HTTP string itself is fairly simple. It's typically a get or a put, and then we have various parameters after this. So in this case, it gets home.html from this host. The ways that covert channels can be set up are to reorder some of the fields, to change the cases, to add new headers, values and flags, to add spaces, and to modify server objects. So an example could be that Bob and Alice could agree that if Bob sends host and then connection, that's a 0, and then on the second request he might send it the other way around, which identifies a binary 1. Another way is that they could agree to change one of the request strings. So if we look at it, the word connection, if they were to agree that it was all in uppercase, then the C corresponds to 0, the O corresponds to 1 because it's changed, N is a 1, and N is a 1 because they have changed their case. Then we have the capital E, which is a 0, capital C, which is 0, then the T and the L have been made lowercase, so we can add that in as a 1, 1. So in hexadecimal, this is 72, 73, and the 73 will correspond to a certain hexadecimal character. Another method might be to add optional fields. So in this case, if except */* is added, then it's a 0. If this one is added, then it's a 1. And then also Bob can add in an actual field, and in this case he's called it Covert Channel. And the way that HTTP works is that fields which are not relevant are basically just ignored by any browser. Along with this, Bob might add some spaces and some horizontal tabs. So it may be difficult to see in this message, but there are various spaces that have been added, and we can see here that we have extra spaces and extra horizontal tabs. So in this case, the message itself is transmitted here and is an H character. Another way that Bob might set up a timing channel is that he accesses a server at a certain time. So we can see here 12 o'clock, 12:30, 1 o'clock, and so on. If he accesses it, then it's a 1. If he doesn't, then it's a binary 0. So we can see here the message is 0, 1, 1, 0, 1, 0, 1, 0. And then that again can be built into a ASCII character. In this part of the lecture series, we'll look at some basic analysis of network traffic. So what are some of the pointers that we're looking for if we have had an intrusion on a network? So it might relate to ICMP activity, and that typically relates to a ping sweep of several hosts on the network. We might also look for DNS activity, where there's some request to a DNS server, which can typically show the start of an intrusion. We might look at the TCP flags, especially for the SYN flag, where the SYN flag identifies the start of any connection. We might also look at basic ARP activity. ARP activity is often the sign of a computer joining a network and then it trying to get out of the local network. And obviously we might look at some application protocol activity. So we might have large amounts of data that we must trawl through, so it's important that we try and find the starts of any event and then be able to trace the timeline from that. One of the most basic flags that we have is the SYN flag, and this is an example using Wireshark for the display filter, and we can define that when the flag is set to a 1, then we can actually see all the data packets relate to that. So if we have a look at Wireshark here, we have it loaded in there, and so let's actually pick the SYN flag equal to a 1. So with this we'll see all the SYN activities inside the data storage. So you can see here that there are quite a few data frames in here. So we have 100,000 data frames, and it's obviously searching through them for any SYN activity. The problem with just going with the SYN flag equal to 1 is that we will also get the currencies of when the acknowledgement flag is also set. So we can see here, we see a great deal of SYNAC activity, and if we want to filter for just SYN on its own, then we can search for the TCP flag equal to SYN and for the acknowledge flag to be a 0. So that gives us a more focused analysis where we can just search for the start of a connection. So you can see here there is a connection from this host to this one here as we see our SYN activity, and this seems to be a connection to an email port, so that the user in this case looks as if they're actually sending an email message. The activity here relates to SSH activity. So we can see here, this is the 2 email ports, and then we can see here a connection to the SSH port. There is now 2 more email messages, and we can see here the finger protocol being used, and so on. So these SYNs allow us to actually get some details on the basic connections that were actually made. We can follow a connection if we require, and this should actually filter for us. So the SYN flag equal to 1 and an acknowledgement equal to 0 is important for determining all the network connections that occurred. Another important focus might be on a certain protocol. So in this case we could filter for the port equal to 21, and that will show us any occurrences of the FTP protocol. So if we have a look back, we can see here that we've actually shown some sort of activity here for FTP, and you can see that the user was the anonymous user. Okay, so we can now filter for purely FTP traffic if we're interested in that. So we can filter for port 21. If we think there's been an intrusion on port 21, then we can actually list all the occurrences. So you can see in this case, this is the FTP server, and then this is the host that has been connecting to that server. And we should be able to see the protocol itself and any TCP packets. So these packets here show the actual FTP protocol working at the application layer, where these ones are standard TCP packets, typically to make a connection or to disconnect it. So we can see here now that we have all our occurrences of FTP. So in this case we have our SYN, and there's an ACK coming back, and then we can actually see the details of any of our FTP traffic details. So we can see here in this case someone is logging in to the system with a username, password, username anonymous, and with a password as given there. This traffic here is taken from a standard DARPA traffic set. Another important port is the UDP port 53, and with this we see DNS activity. So DNS activity is typically a sign that a user is asking the DNS server to resolve the name of a domain. So in this case it might be for the Microsoft.com domain, and we see a standard query. And then after it we get a DNS response where it will actually resolve the IP addresses of the servers. So we can see in this case this is the reply back from the google.com domain, and these are the IP addresses which could be used to resolve that domain. So UDP port 53 is often a good place to start to see the basic network trace. So we can see here this is an example of what the DNS reply returns, and defines a number of IP addresses. We can also search for certain hosts that we're interested in. So in this case we have searched for 68.37.75.158. So at any time we can actually define an IP address that we're interested in, and so we can say 66.7.248.153, and then it should filter through and give us any activity from that specific host. We can search from the communications between two hosts. In this case, if the IP address is equal to the one we searched for before, and if the IP address is equal to 10.0.1.207, then we can get it to list. So this allows us to actually focus in on the communications just between two machines. So we can see in this case we can actually see there is some email communication, email sending between the two nodes here. This is a standard type of trace for SMTP. So we look back at our trace and we can see here that we have filtered for this individual node, of which we can see FTP traffic, and we also see some SMTP traffic here. We can also look for certain MAC addresses on the network. So each data packet itself actually has the Ethernet details. So we can see here a source MAC address and a destination MAC address. So we can actually search for a specific MAC address if we require. So we can see that the source, the Ethernet.source is equal to 0.0C4F A358 and then 60. and this should search for this specific MAC address. MAC addresses can often be spoofed, so they can't be taken as a completely credible source of identity of a machine. So the MAC address can be searched, so we can see in this case that the address that we're actually looking for is this one here. So this is identified probably as the MAC address of the gateway. Any communication that we have between our host and the internet, the MAC address will typically be of the source port of the router in which we connect to. The IP address will be for the destination, but the actual destination port, MAC address port, will be the MAC address of the router port which we use as a gateway. Also, data frames coming back in will have a source port equal to the MAC address of the gateway. So we go back, and unfortunately we haven't found anything there. I think we can look for the destination. If at any time we forget what the actual expression is for the filter, then we can bring up our filter expression and then find the protocol that we're interested in. So in this case we're interested in Ethernet, and it's eth.dst. Still doesn't seem to like that. There we go. Okay, so this shows another example using the source Ethernet address. We also see broadcasts on the network, and a broadcast typically happens when there is some ARP activity. And the ARP activity gives us a basic fingerprint of someone trying to possibly discover the network. So we can see here this looks a strange type of activity where this node is continually asking for nodes on the network. So this might be a trace of an intruder who is scanning the network for these hosts. So the Ethernet destination of all Fs gives us our broadcast traffic. So we take that and then we define some broadcast. And we can see here that we're starting to get some broadcast traffic, and the broadcast traffic might give us a pointer to some scanning activity of the network. So this type of activity might look strange, but actually there's a reason for this, in that 10.0.1.1 is actually the gateway for this network. And what's happening here is that when data packets come in or requests happen for these machines within inside this network, then the actual gateway is asking what the MAC address is of that actual host. Once it gets the request, the reply back, then it can update its ARP cache, so it does not need to re-request it for some time. So we can see here a re-request happens sometime later because the gateway has aged out the old ARP entry. So an ARP opcode can also give us identification of ARP activity. We can see here that we have the ARP protocol. And basically how it works is that if this machine wants to get out of the network and communicate with this machine, then it must acquire the MAC address of the gateway to be able to communicate out. So it knows what the IP address is of the gateway. So in this case it's 1.1. So it sends out an ARP request inside its own domain to all these nodes, and they listen to it. The router will stop the ARP going over the device, and then the port which has that address will actually return back only to the host who asked it what its MAC address actually is. So the ARP that goes out is who has 1.1 tell 1.102. So the reply comes back only to the device who asked for it, and it updates its ARP cache. Once it has this address, it can then communicate with the gateway and actually send to an external node. Same thing can happen when a data packet comes in for a node which is on the network. The router looks at the IP address, checks in its ARP cache to see if it has the MAC address for that IP address. If it hasn't, it'll send out an ARP request to the network, and then hopefully it will actually resolve it. So ARP is a beautiful protocol which allows the internet to actually change at an instance. So we can see here, this is an example of an ARP request. Who has 1.1 tell 102. So we can see here that the source and the destination MAC addresses relate to the source MAC address of the host which is asking for it, and then we broadcast across the whole of the local network. And this is an ARP request. There are various details within there, and it gives the MAC address of the sender, IP address of the sender, and the target IP address for the request. A reply that comes back in will look something like this, where the node actually says that I'm at this MAC address here, and we can see the reply, ARP reply, that actually comes back. Another type of activity that might look suspicious or might show us some surveillance is related to ping activity or ICMP. This could be related to a trace route or a ping. So in this case we've searched for ICMP type. ICMP.type, and then we can actually see any activity related to that. So we can see a ping request here followed by a ping reply. So you can see that IP is encapsulating the ICMP packet. So we're not using the IP, the TCP protocol here. Inside the protocol field of the IP packet, we have a type 1 which is ICMP. Same again, ICMP. And then inside the protocol itself, we actually have a ping request, and then we have a ping reply. So this is an important thing to trace for, in that it could identify some form of port sweep, of host sweep. Okay, so there's our ping reply here coming back with an ICMP. We can also search for high-level protocols, such as for FTP. We can do the same for most other application protocols. So we define if HTTP request.method is equal to get, and that will allow us to get any get requests for HTTP. So we can see examples here, and this is when the request method is not GET. So in this case we can see post activity and notify for HTTP. And we can do the same for any protocol. So we could do the same for FTP type activity. So we can say for FTP request or FTP.response, and then we can actually search for that protocol. So FTP.request is one option, and we can define ftp.request.command is equal to user, and this will allow us to see whenever a user has actually logged in to an FTP server. And we can see in this case, with inside this network traffic, there is a great deal of user anonymous traffic logins. This can look suspicious in that an anonymous user is maybe trying to hide their tracks. So we can see here, these are all the requests. So we have IP, we have TCP, because FTP is built on TCP, and we can see the details here are that we use the user command, and then the argument in this case is anonymous. So these are continual anonymous logins. We can follow the TCP stream if we require from any of the events. We can see here that Wireshark is building up the basic search filter for us, and this will give us a timeline of when the user logged in with anonymous and until the end of the FTP connection. We can also do it for not user, and we can see all the other commands which have actually been used for FTP requests. So a useful tool for an investigator, and we can see here this is the example. So in this case the user has logged in with anonymous. This is a port negotiation with inside FTP. They have changed the working folder to mailing list. Then they have went into archive and then into music, and the list command is gives a list back of what's in that folder. Then the user has returned this file here and then actually quit. So each of these are the data packets associated with that. So the stream is important for actually showing the communications to the server and back again. So this shows the trace here. And we open up Capture 2 and get rid of the filter. And we have our activity here. So we might search for the initial SYN. So in this case we have the start of a connection here, and then we can follow the basic stream from there. And we can see here that the user logged in with anonymous with some password. Then there was some messages came back. There is a port negotiation here with an FTP, and then the user themselves have tried to change to one directory above. Then they have went into the bin directory and they have listed what's in there. They went back up and then quit. So this might look like malicious intent because an anonymous user is trying to go up to a higher level directory and into the bin folder. Okay, so we'll have a look at an example of an analysis, some of the analysis tools. So we can see here that we have 100,000 data frames in here, and it's obviously difficult to find any traces of activity from the actual the data frames themselves. Luckily, we have some basic pointers. We can look at the basic summary of it to see how long the timeline is. So you can see in this case it's 1400 seconds. And then we can also look at the protocol hierarchy. So the protocol hierarchy will give us an idea of the basic protocols, IP, TCP, even the application layer protocols. So that will give us some idea of the activity within inside the network traffic. Often this can be used in some sort of anomaly detection system. So you can see here that virtually or all the frames were Ethernet, and then we've got mostly IP data packets, a few other ones. So we have some ARP in here too. But then within the IP packets, we can see that 98% of them were TCP packets. There's a few routing packets there, and there are some ICMP packets. So you can see there was 46 that could be related to a ping or a trace route. Within TCP, we can see there that most of the traffic was actually HTTP. There was some email, a little bit of SSH, some data, and a tiny little bit of telnet, along with some FTP traffic. So these are good pointers to actually see what type of activity was in there. We can see most of the UDP traffic was related to the local Windows network using the NetBIOS service. And then there was some loopback information there. So we can actually have a look to see what the endpoints were of the actual conversations. So we can see where the basic data has went from and to. It just takes a little minute to generate this, because it's obviously got to analyze each of the machines. The data here that we're using is from the DARPA traffic that was created around 2000 and can be used to basically train on and to identify threats with inside the traffic. So let's see if we can get our trace now. We can see here that we have one trace. These are the endpoints. So we can see here for Ethernet activity, those are the MAC addresses and the number of transmitted bytes from each. Slightly that this is the router port, and these are more likely to be the nodes on the network, especially for this one. But we can see here that these are the addresses and the amount of bytes transmitted. In this case, only the transmitted data has actually been listened to, and that's why there isn't any received data here. So we can see here this gives us a list of all the data that was actually sent and received. We see for our local network we actually have some local traffic which we have captured, and then for TCP we can look at the basic protocols that were actually causing that, and then what the actual host addresses were for those protocols. So that's a useful way for us to actually determine any of the activity. We can also look at the basic statistics for the graph of the data packets. It just takes a little minute to generate. And we can see here the activity across the basic timeline, and this will often give us ideas as to when possible threats occurred. Another useful tool that we can use to analyze the basic events on the network is with a flow graph. So in this case we'll actually see all the basic flows of data in a graphical way. So with this we can actually see when the SYNs actually happened, when there was a SYNAC, when there was a finish flag to the actual connection. It just takes a little minute to generate. And it's from these points that we can actually determine when a conversation actually started, and then we can trace on from there. So the data itself there might be a great deal of data, so it's important that we set up these filters to efficiently investigate occurrences, especially so that we can set up the security in the future to be able to stop any threats on our systems. So we'll actually just stop that, and we can see here that we can actually determine when the basic events happened. So we can see there this node sent an HTTP request to this node. There was then a SYN, went from this node to this one, and then so on. So this gives us a basic timeline of activity between certain hosts. So we can see here there's a lot of activity between port 80 here for these hosts. And we can look at other hosts too, especially for broadcast traffic and so on.